distinguished guests, ladies and gentlemen, it is my great pleasure to talk about the researches in Kamioka, neutrinos and gravitational waves here in University of Perugia. This morning, I want to talk about the neutrino research in Kamioka. Then I want to talk about the recent activity trying to observe gravitational waves. Now, first I'm going to talk about neutrino research. And before going to talk about our research, I want to tell you what are neutrinos. Neutrinos are elementary particles like electrons and quarks. They have no electric charge. They have, like the other particles, three types, namely electron neutrinos, muon neutrinos, and tau neutrinos. They are produced in various places, such as the Earth's atmosphere, and they can easily penetrate through the Earth. And I just want to tell you that in the very successful standard model of particle physics, neutrinos are assumed to have no mass. Now, I want to tell you about our activities in Kamioka. The first experiment I was involved was the Kamiokande experiment. Kamiokande was constructed to observe proton decays, and the experiment began in 1983. And at that time, the predicted lifetime of proton was about 10. Maybe I can get water here. Thank you. The predicted lifetime of proton was about 10 to 30 years. So we wanted to observe the decay of protons with the Kamiokande experiment. It was a large water detector with the diameter of about 16 meters and the height of also 16 meters. And if a charged particle propagates in the water, a faint light called Cherenkov light is emitted. And these lights are detected by photodetectors instrumented at the wall of the detector. So we wanted to observe proton decays. However, soon after the experiment began, we realized that there's no evidence for proton decay. Instead, we observed neutrinos produced in the atmosphere. Well, you may know there's cosmic rays coming into the Earth from somewhere. And these cosmic ray particles interact with the air nuclei and produce pions. And then these pions decay to muons, then to electrons. And during this decay chain, neutrinos are produced, and they are observed in underground detectors. And because this is a serious background to proton decay searches, we had to study these atmospheric neutrinos. And during the study of atmospheric neutrinos as the background for proton decays, a significant deficit of atmospheric muon neutrino events was observed. That was 1988. Well, at that moment, we had no idea what was going on. But just as a possibility, we thought maybe this data suggests that neutrinos oscillate. Well, I said neutrinos oscillate, but what I have not explained what it is. Well, if neutrinos have mass, neutrinos change their type from one type to the other while propagating in the vacuum. For example, a muon neutrino produced at a point may change to tau neutrino after traveling some distance, and if they travel further, tau neutrino change back to muon neutrino. And that way, neutrino type changes continuously while propagating in the vacuum. This is the neutrino oscillation, and this was predicted by Pontecorvo, Maki, Nakagawa, and Sakata more than 50 years ago. So from the beginning, we thought that the data might suggest neutrino oscillations. But with the Kamiokande experiment, we are unable to get any clear evidence for neutrino oscillations. And it was clear that we needed a much better, much larger detector. That was Super Kamiokande. Super Kamiokande is a much larger version of Kamiokande. It is an underground water detector with the diameter of about 40 meters and the height, again, 40 meters. And it contains about 50,000 tons of water in this tank. And this is an international collaboration from 10 countries, and we have about 160 collaborators at this moment. Anyway, this experiment was approved in 1991, and we started the experiment in April 1996. This photo shows the filling of pure water into the Super Kamiokande tank. And this photo was taken in January 1996. And from the beginning of this experiment, we continuously observe atmospheric neutrinos. And of course, we wanted to know if the deficit of atmospheric neutrinos is due to neutrino oscillations or not. Then we thought, what should be the evidence for neutrino oscillations? We thought this way. Neutrinos are produced in the upper atmosphere above us, maybe 10, 20 kilometers above us. They come to the detector, and they only travel 10 to 20 kilometers. Therefore, maybe they have no time to oscillate. However, neutrinos created in the other side of the Earth have to travel long distances, typically 10,000 kilometers. Therefore, these neutrinos might have enough time to oscillate. Therefore, if we observe the deficit of muon neutrinos in the upward going direction only, that can be the evidence for neutrino oscillations. So from the beginning of the Super Kamiokande experiment, we carefully analyzed the data. And in fact, in 2 years after the beginning of the experiment, we were able to show the data from Super Kamiokande at the neutrino conference in 1998. This slide is a copy of the presentation at that conference. And here, we showed the genius angular distribution for electron neutrinos and muon neutrinos. Electron neutrinos are in the upper figure, and muon neutrinos are in the lower figure. And cosine theta 1 means downgoing neutrinos, and -1 means upward-going neutrinos. These neutrinos came, then these neutrinos are produced in the other side of the Earth. So they traveled long distance, and you can see there is a huge deficit of upward-going muon neutrinos. And in fact, this is what we expected for neutrino oscillations. Neutrinos produced in the other side of the Earth propagate in the Earth, and while propagating in the Earth, they change their type from muon neutrino to tau neutrino, muon neutrino, tau neutrino, and so on. And therefore, when they come to the Super Kamiokande detector, only half of them are muon neutrinos. Therefore, there is a huge deficit of muon neutrinos coming from the other side of the Earth. So this was the evidence for neutrino oscillations. And this data told us that neutrinos have mass. But, well, maybe you may ask, well, since these are the particles, it might be natural to have finite mass. Why it is important to observe the neutrino mass? Now, I want to tell you why we think that the finite neutrino mass is important. Here, I show the masses of charged leptons and quarks. Now, well, these are the masses of these 9 particles. Now, please be careful about the horizontal axis. 1 unit shows 100. So if you have 2 unit separation, that is 10,000. 3 unit separation, that is 1 million difference. Now, I want to add the neutrino mass on this plot. They come here. So you immediately notice that the neutrino masses are much smaller than the other particles' masses. And we think this is important. In fact, if you read the figure carefully, we notice that the neutrino masses are approximately or more than 10 billion or 10 orders of magnitude smaller than the corresponding masses of quarks and charged leptons. So neutrino masses are extremely small, and we believe this is important, and we believe that this is the key to better understand elementary particles and the universe. So this is what we did in neutrino physics. And in the remaining time, we want to talk about the new research in Kamioka, that is the gravitational waves. Well, Albert Einstein predicted gravitational waves almost about 100 years ago, 1916, based on his theory of general relativity. And this is the image of the gravitational wave generated by binary black holes. And, well, Eventually, these binary black holes merge and a new, heavier black hole should be generated. And in fact, gravitational wave signals of the merger of binary black holes were discovered in 2015 for the first time by the LIGO and Virgo collaborations. So we are in an extremely interesting era. It is the beginning of the completely new astronomy. So now in Kamioka, coming back to Kamioka, Kamioka has been contributing a lot to neutrino physics, but we also realized that underground is very important for basic science. Therefore, a new detector called Kagura on gravitational wave is under construction in Kamioka. And in this picture, in this figure, I want to show you the outline of the Kagura interferometer. It is an underground 3 kilometer by 3 kilometer interferometer. We are constructing this interferometer now. Okay, let me summarize. Kamioka has been contributing a lot to basic science in the last 30 years and is expected to contribute more in the future. In the early 80s, Kamioka began trying to observe proton decays and unexpectedly observed atomic neutrino deficit. Subsequently, in 1998, Super Kamioka discovered neutrino oscillations. I think I was extremely lucky because I was involved in the excitement of the discovery of neutrino oscillations from the beginning. Now, Kagura is a new project trying to observe gravitational wave signals. We are most excited with the newly opened gravitational wave astronomy. And well, of course, we'd like to unveil the secrets of the universe with neutrinos and gravitational waves. Thank you very much.
Nunc recede.